Suprita, I have made you host.
Okay, noted.
Prof. Tanaka, good afternoon.
Hi, good afternoon.
Good afternoon. Today, Rashid, he will chair the session.
The six
Rashid, Sbia.
talks, short talks, right?
Yeah, short talks, yes.
Mhm.
So we three of us will continue to judge.
Yep. Who will the chair?
Rashid Sbia.
Okay.
Yeah, he will be the chair, yes.
Hello, good morning.
Hi, good afternoon.
Good afternoon.
Good afternoon.
How are you? Just on time?
Yep.
Okay. So I will be chairing this session, isn't it? The
Yeah,
one.
please. Yeah, please. Thank you.
So the speaker is, I think it's there. Sorry. So good afternoon. I am Rashid Sbia from SQ University in Oman. So I am happy to chair this today's session. So the session F. We will have 7 talks. So we start with the first one. Timothy Ng from NTU University in Singapore. So, and his talk will be about photodetectors that exhibit memory and adaptive capabilities. So, is the speaker around? Timothy, are you ready?
Well, I don't see Timothy in the participants.
William,
Sorry?
are you ready? If not, we can move to the next speaker.
Yeah, I'm ready.
Okay, okay.
Yeah, William is
So-
ready. So,
William?
Yeah.
We move to second. Okay, I can see you. William, how are you?
Hello. I'm
Okay.
good. How are you?
Yeah, thank you. So the talk is about synthetic SAF domain wall devices. Domain wall device as artificial neuron for neuromorphic computing. So this is synthetic antiferromantic coupling, isn't it?
Yeah.
SCF domain wall. Please go ahead.
Okay. Can you see my slides?
Yes, I can see it. Professor Prem, how long is the talk?
so
So-
12 minutes for the talk and 3 minutes for Q&A.
Okay, okay,
So we finish in about 15 minutes.
okay.
Okay, thank you.
Shall I start?
Yeah,
Timothy,
please
you
go
can
ahead.
start now.
Good afternoon. Thank you for giving me the opportunity to present. My name is William from NTU. I'm going to talk about artificial neurons for neuromorphic computing. Neuromorphic computing is a more power efficient platform for AI because it is modeled after the brain, which consumes less power than your typical state-of-the-art supercomputer in performing the same things. For example, in audio recognition, visual recognition, verbal communication, the brain consumes less power. And so since neuromorphic computing is modeled after the brain, it has 2 main components, the neuron and the synapse, which is the processor and the memory respectively. So far, there's been more focus done on synapses. But in this talk, I'm going to focus on artificial neurons, specifically domain wall-based neuron. Domain wall-based neuron should exhibit these 3 properties. It's called the leaky, integrate, and fire properties. I'm going to explain them in the context of a domain wall device. The first is the integrate function, which is the ability to push the domain wall by applying current. And then the firing function, which happens when the domain wall has passed a certain threshold position, then I should see a change in the read signal. And finally is the leakage function, which happens in the absence of current. Then domain wall should automatically return towards the starting position. That is the leakage function. And so in our research, we want to achieve the integrate and the leakage properties first. Firing function comes as future work. So how do we achieve the integrate and leakage function? Is by using a synthetic antiferromagnetic structure, whereby the free and pin layers are mostly antiferromagnetically coupled to each other. I say mostly because there is a region on the left here that we want it to be ferromagnetically coupled so that we can nucleate a domain wall without having to apply any magnetic field. So the integrate function can be achieved in this case by a spin transfer torque. We apply some current. Current is polarized by a region on the left here, and then after that pushes the domain wall towards the right. The leakage function is achieved once current is switched off, and then by virtue of the antiferromagnetic coupling between the top and the bottom layers, the red region would expand, which automatically pushes the domain wall towards the left. So we did some simulations to demonstrate the integrate and leakage functions. graph on the right is a domain wall position against time graph. The initial position, which is at the 128 nanometers mark, corresponds to this point here in the drawing. And then 384 is the threshold position corresponding to this point in the drawing. So as you can see in the upslope portion of this graph, that happens when current is being applied and domain wall is pushed towards the left. That's where the position increases. And then once it reaches the threshold position, current is switched off, and then domain wall automatically comes back down towards the initial position. The stronger my antiferromagnetic coupling, the faster it comes down. To more clearly illustrate my point, here is a video where current is being applied and then domain wall is pushed. That's the integrate function. Once it reaches the threshold position, it automatically comes back down. This is in the absence of current. So automatically comes back. That's the leakage function. And so in the simulations, we were able to demonstrate the integrate and leakage functions. Now we move on to the experimental work. So experimentally, we use this cobalt palladium multi-layer sample where the top is the free layer, the one with the 3 multi-layers free layer, and the one with 10 multi-layers is the pin layer. As you can see at the red color out of plane hysteresis loop on the right here, this is a SAF sample. And so using optical lithography, I fabricated a micro wire that is 100 micrometer long, 5 micrometer wide. The thickness is just the thickness of the entire sample minus the substrate. And I applied a total of 10 pulses. Each pulse is around 2 seconds from each other. I represents the current strength. PW is the pulse width. So the current strength is varied from 0.01 to 0.03 amperes. And then the pulse width goes from 1 microsecond all the way to 6 microseconds. I've tried every single combination, but in this talk, for the sake of time, I'm only going to specify just a few cases. First of all, I apply a really strong saturating field in the plus Z direction so that I saturate everything. That includes the bottom pin layer as well. And then after that, I immediately reduce it to around 2.3 kiloostate, because at that point, I can nucleate the domain walls in the free layer. Once the domain walls are nucleated, then I apply current pulses and then observe what happens under curve microscopy. So in this case, the current strength is about 0.03 ampere, and then the pulse width is 6 microseconds. Now, this is a video, and it will be important to note this pulse word here, because I'm going to be flashing this pulse word every time. And this pulse indicates I'm applying current pulse. And then you can see what happens to the domain wall. Okay, so I apply a current pulse, and then the domain walls are pushed back. Here is some snapshots from this video. And you can see, once I apply the current pulse, the domain walls are pushed back. That is the integrate function. After some time, it comes back by itself. That is a leakage function. But one interesting observation is that the domain walls are moving in opposite directions. That is not indicative of the spin transfer torque, because if it's spin transfer torque, the domain walls should move in tandem. But in this case, they're moving in opposite directions. And so to further investigate this, I was thinking, how about we flip the direction of the current pulse so that I apply it in reverse direction and see what happens. So these two are also videos. And for these two cases, the pulses, the pulse strength, the current strength is the same, 0.03 ampere. The pulse width is also the same, 6 microseconds. And if you look at these two videos, you'll notice that the domain walls are pushed in opposite directions. So there is no difference in the current pulse direction, which means the dominant driving effect is not due to spin transfer torque. So one possibility as how this can happen is the Joule heating. So to determine whether Joule heating is a significant effect or not, we conducted some minor loop measurements. This black curve here is the reference case. It's the one without any current. And then the rest, these all have current pulses. The current details are right here. If you look at this table, HC is the coercivity and then the exchange field. So if you look at just the coercivity first, you notice there's a lot of difference. There's a lot of difference in the coercivity. And that indicates the effect of Joule heating, because heat can decrease the coercivity of the sample. And then the next point is the reduction in exchange field. Now, even though this exchange field doesn't really change as much as the coercivity, you can tell there's some sort of decrease there. And so the decrease there indicates there's a weakening in the antiferromagnetic coupling between the free and the pin layers. So this is also possible due to heat. And so the logic is that with Joule heating, or heat in general, the antiferromagnetic coupling strength would reduce, will be weakened between the free and the pin layers. And because of that, and also because of the fact that I'm applying a magnetic field in the z direction all the time, the Zeeman effect eventually dominates because antiferromagnetic coupling weakens. And because of that, the plus Z domain, which is the red color here in this drawing, would expand. So domain wall gets pushed back. So that's what we observe in the videos and also the snapshots. That gives us our integrate function. As for the leakage function, that is because of the antiferromagnetic coupling. After a short amount of time, the heat will dissipate. And once that happens, the Zeeman effect no longer dominates. Once it no longer dominates, then the blue region, the blue domains here, which are the minus Z domains, would expand. So then domain wall comes back. So the key achievements is in the simulations, we achieve the integrate and leakage functions. The same goes for experiments. And even though the integrate function is achieved by Joule heating, you notice the current density is actually comparable to spin transfer torque. So it is not high, it's okay. And in the future, we want to achieve the firing function. We can do so by implementing a magnetic tunnel junction stack. In that case, when the domain wall passes the MTJ, then I can see a difference in the tunnel magneto resistance, which is a change in the read signal. And then to improve the speed and reduce energy, we can scale down the device. We can use electron beam lithography to make a smaller device. And then to further reduce current density, we can use copper iron boron because it has lower coercivity, so that requires less current as well. And that's all. Thank you for your attention.
Thank you, William. Now the paper is open for questions. You have any question?
Ramo, please ask.
William, I have one question.
Mhm.
If you can go back to slide number 12. Okay, I noticed that, you know, in the down domain, that's been the dark one, you have still few small domains inside. You have some explanation. It is not completely down and up. So you have still within the big domain, you have small domains.
Mhm.
Can you see that? Yes, those, you know, white.
You mean like this kind, right? The small
Yes,
domain?
yes, yes. So it is very difficult to see. You have sharp domain wall between two large domains.
Yeah, so for those cases, I've thought about it. It's probably due to the crystalline structure of the cobalt palladium outer layers. Because of that, you don't get the exactly nice domains. I think in that case, right, if you substitute it and use like a cobalt iron boron when it's a more amorphous structure, you wouldn't notice these kind of things.
Yeah. Okay.
Ramo, just unmute and ask your question.
Yeah, actually, I have this question regarding the domains, the small domains. And the other question regarding like, yeah, for this particular slide, like when you're changing the current direction along the track, okay, you see in one case, the domain is contrasting, in the other case, domain is expanding, correct?
Yeah.
So if you consider like Joule heating, which is like, it is a magnitude, I mean, Q is called I square RT, so it should not depend on the direction of the current. So why do you think like it is because of the Joule heating? Because it doesn't take consideration of the polarity of the current, right?
Yeah, so the idea was because I observed that at the start, I observed that the domain walls are being pushed in the opposite directions. So I thought this effect could be non-direction specific.
Because irrespective of the current polarity, the domain compression should be the same. I mean, if it is Joule heating.
Yeah. So that is what this study here shows as well, because the forward and reverse directions give this similar things, right? So this is just to show that it is because of Joule heating. It's to further show that it's because of Joule heating.
I mean, you meant to say like is the direction of the current, you are getting the same behavior, is it?
Yeah, that's the idea.
Okay, let's thank the speaker again. So we can move now to the next talk, which is will be presented by Sri Lakshmi from NTU. And his talk is about optoelectronic transistor sensitized using perovskite quantum dot for synapses.
Sri Lakshmi doesn't seem to be here, but Timothy has come back. Maybe we can ask Timothy.
Okay, we can move to the first speaker, isn't it?
Yeah.
Yes, I'm here.
Okay,
I'm
okay,
so sorry.
okay,
Yeah.
okay. Okay,
I'll be
Timothy
sharing
are
screen.
here.
Yes.
Okay, it's about photo detectors, sorry, that exhibit memory and adaptive capabilities. Are you ready, Timothy?
Yes, I'm ready.
Yes, yes, yes. You can start now.
Thank you everyone for joining this presentation. I'm Timothy, and I will be talking about electrochromic transistors as adaptable photodetectors. So with the development of sensors, sensors have become more sensitive. It has also become more accessible with various types of sensors. They are commonly used in Internet of Things, and very much digitalization is enabled by memory improvement in memory storage technologies. In these applications, sensors are responsible for extracting critical information from the environment. They allow this information to be converted into electrical signals. Then we read them accordingly. Sensors are transducers. They convert light information into electrical signals. So this is done by a simple photoconduction principle. So the conductivity of the semiconductor is initially, it can be monitored by a small voltage. So in the dark, the low concentration makes this semiconductor layer resistive. However, with light, carrier concentration increases. Hence, the current also increases. So this is known as response and is calculated by the differences between the two currents. So by measuring response, we can identify the intensity of light. However, most of these high response sensors are noisy in nature. And while the less noisy sensors have very poor response. So depending on the situation, a high response sensor or a high signal to noise rate sensor will be preferred. The biological sensory systems like the eye mitigates this issue by dynamic adaptation. They first have dedicated photoreceptors, such as the cones and rods. In the bright conditions, the red-green response is critical for hunting and gathering, while the cones are active providing this color sensitivity. However, in the dark conditions where low noise is crucial for danger detection, rods are active, providing this contrast sensitivity. So these adaptations are done via complex biochemical process known as bleaching. So again, dynamic adaptation is enabled by dedicated photoreceptors and chemical reaction such as bleaching. So what is sensory adaptation in electro devices? It is applying biologically inspired principles to build devices that can effectively detect stimulus or capture information. We use sensory adaptation concepts like photoreceptors, bleaching, and phototransduction. Eventually, we make sensors that are not only sensitive but also capable of learning and adjusting. So one of the principles that we can use is the field effects. The field effects can provide modulation in photo response, can be used to increase or decrease the photo response. Secondly, we can add photosensitizers to shift the wavelength peak or to extend the absorption spectrum. Sensory adaptation actually requires the reversible switching between in the photo response. So requires on-demand tunable responsivity. So field effects and photosensitization alone are insufficient and requires electrochemical or chemical changes. So we introduced a device. Electrochromic devices are not new. Electrochromic devices are devices that can switch in terms of spectral absorption. So here the device structure is very simple. We have a reactive sputter molyoxide onto a FTO substrate. We then add the ionic gel, morpholine based gel onto the molyoxide, and then we cover it with another FTO substrate. So by applying a positive voltage on the top electrode, we can effectively reduce the molyoxide and accompanied with the intercalation of the lithium ions. So this lithium dope molyoxide has enhanced absorption, in particularly the higher wavelengths at green and blue. So electrochromism is the change in optical absorption spectrum via the reduction and oxidation of molyoxides. So we propose to use this principle into a transistor and then use this as a photodetector device that can electro-adapt. So the structure of an electrochromic transistor is very simple. The source drain electrodes are made of ITO, and then the molyoxide is also reactive sputtered. The operation of an electrochromic transistor is very simple. When a positive gate voltage is applied on top, lithium ions drip accordingly. This forms the electric double layer at the molyoxide ionic gel interface. This field effects electron accumulation in the molyoxide semiconductor then turns the transistor on. However, besides that, some of the lithium ions are intercalated into molyoxide layer. When the gate bias is removed, while the electric double layer can be dispersed via diffusion, some of these lithium ions remaining will result in a permanent increase in conductance. So the device is monitored with a small voltage, VDS voltage of 0.1. We apply a gate voltage to modulate the conductance. So we can see here we have a train of 16 pulses. We can modulate, increase the conductance states accordingly. We can also apply a negative pulse to extract lithium ions away and suppress the conductance states. So what we have shown here is a deterministic modulation of conductance states. We will subsequently also show that this is accompanied with optical absorption spectrum change. We call them spectral states. So here, the optical absorbance after each pulse can also be seen. We can see that the absorption spectrum, there is an enhanced absorption at the higher wavelengths, such as the red and green region. So this is accompanied. This is attributed to the intercalation of lithium ions. We can see here from the SPS spectrum that lithium ions can be introduced or extracted away. The intercalation of lithium ions is accompanied by the reduction of molyoxide from 6+ to 5+. So the photo device conductance can be monitored with a VDS of 0.1, and then we shine 3 different lights: red, green, and blue. We can see that initially the sensor is resistive in nature. When we shine light, the current increases. We also have 2 different states. The desensitized states refers to the undoped molyoxides, while the sensitized states refers to the doped oxides. We can see that the undoped oxide exhibits response only to a blue wavelength, but the doped molyoxide responds to all 3 wavelengths. So the sensor response when plotted against the stimuli intensity, we can effectively calculate the gradient, which gives us the responsivity. So we can see that there is a low modulation of blue sensitivity, but a large modulation of the green and red responsivity. So what we have shown is a large responsivity towards the higher wavelength, and that's why we show selectivity of tunability. To understand the switching, we need to understand the electronic structure as well. So in simple state, when we measure the valence band spectrum using UPS, we can actually see that there is a evolved state which corresponds to a B2G state in the reduced offsets. So this state is responsible for the absorption of higher wavelength and also increased conductivity. This is also observed in capacitance measurements. So we have observed a fluidic state which is responsible for the higher conductance and enhanced responsivity. So subsequently, we evaluate this adaptation in the human eye with our photodetector array. When it is bright, we can see that we can change the device to a photomic mode or the sensitized mode, such that it shows high color sensitivity but low signal to noise ratio. While it is in the dark, we can actually change these states to a scotopic mode, which is not color sensitive, but show high signal to noise ratio. So we have an on-demand tunability of color sensitivity and contrast sensitivity that we use to emulate adaptation. So in summary, we have a problem is that devices are either high response or low or very noisy. So we need to have adaptation that allows us to have the best of both worlds. So we need to tune the spectral responsivity, and to solve that, we use electrochromic transistors. With that, we have shown electrochromic switching in this sensing layer. We also show transistor operation and memory storage in this transistor configuration, transistor device. Lastly, we use it to the tunable photoresponsivity to emulate this scotopic and photopic vision. And thank you.
Thank you, Timothy.
Yes.
Now it's time for a few questions. Any question?
Can you explain the novelty of your work?
Yes, electrochromic transistors are not new in particular. We have seen them in organic electrochemical transistor as well. However, the difference is so transistors. So the photoresponsivity of these electrochromic transistors have not been tapped into, while electrochemical transistors have been used as a transistor. To store memory. The modulation of the photoresponse has not been demonstrated. So while the enhanced absorption at the higher wavelength is shown in these electrochromic displays, they have not shown yet to show that this enhanced absorption will also lead to enhanced photoresponse. So here we actually show with UPS and also capacitance measurements that this enhanced absorption or this particular field D state will actually provide more electrons for during the photo conductivity as well.
Okay, thank you.
Oh, thanks.
The next speaker is here. Sri Lakshmi is here, so we can move on.
Okay, thank you.
Prof. Svi, your mic is muted.
Oh, sorry. Okay, next speaker is Sri Lakshmi from NTU University. His talk is on optoelectronic transistor sensitized using perovskite quantum dot for synapses. Sri Lakshmi,
Yeah, hi, Prof.
hi. You have 12 minutes.
Sure. You guys can able to see the slide, right?
Yes, you can. Can you put a slideshow?
Yeah. Now, sir.
Very good. Yes, now
Yeah.
it's clear.
Okay. Thank you so much. My name is Sri Lakshmi Subramanian Periyal. My topic is optoelectronic transistor sensitized using perovskite quantum dots for synapses. So this is the outline of the presentation. To start with, I will introduce neuromorphic computing and share some of the research gaps and objectives, followed by the synaptic transistor device fabrication and some research and discussion. Finally, I'll conclude with the summary. So in everyday applications, we have seen quite a lot of artificial neural network applications around us. For example, Siri from Apple, facial recognition, etc. Artificial neural network uses real world data for training. If we want to implement the similar technology using conventional computing, it is difficult because of certain challenges. Here, the CPU and memory are connected by the bus. The bus has become the bottleneck for this data-intensive applications. To resolve this issue, we can take inspirations from the biological systems such as human brain. Human brain has enormous amount of neurons. During brain activity, any neurons, so for any brain activity, one neuron sends the signal to the other neuron in the small junction called synapse. Here, the neuron sends the signal and synapse stores it. So if we build an architecture taking inspirations from the human brain, then we can build a non-human computing where the CPU and memory are single unit. Here, the bottleneck issue has been completely resolved. Because the neuron sends the signal, we can consider it as CPU and synapse as memory unit because it stores it. Thus, the neuromorphic computing is to build electronic devices that works like the human brain. So we can take a look at how the neural network works. The neural network has essentially two parts, neurons, which are referred as the nodes, and synapses, which are referred as the memory because it carries weights. I will explain this by using an example. For example, if a handwritten digit number 8 is introduced into the neural network predicts its output based on the previous training. Some of the nodes that carries information about number 8 will be activated, which strengthens the corresponding synaptic connection. Thus, the output 8 will be generated. So we would like to implement a similar technology by building a device called artificial synapse. If we take a look at the existing technology, IBM has recently released the TrueNorth processor with 10 power 6 synapses using 10.9 transistors, but it has its own challenges. The number of transistors required is too high with large number of interconnects and also high power consumption. Whereas if we compare it with the human brain has enormous number of synapses. So we need to have a single electronic device which is equivalent to the complexity of the human brain. For that, we need to look into the new materials and new principal devices. So for emulating the artificial synapses, one of the material strategy is to have the two-terminal membristors. Two-terminal membristors are membristors with metal insulator and metal stack. So when we have the set voltage, the device goes from the low resistance state, and when we reset it, it goes to the high resistance state. If we take a look at the current voltage characteristics, we can see that the current is changing abruptly. So this kind of abrupt transition is not good for the it's not good in terms of neural network point of view, because it will be able to have only limited states. Also, the simultaneous reading and writing operations cannot be performed. So these challenges can be overcome by using three-terminal transistors. Three-terminal transistors essentially have three terminals: gate, dielectric, and semiconductor, along with its source drain contacts. When we have a source, when we apply the source gate voltage and source drain voltage, we will be able to accumulate charge carriers in the semiconducting channel, and thereby the device goes to the on state. When we apply the reset voltage, the device goes to the off state. So the performance of the 3-terminal transistors can be studied by using the transfer characteristics and output characteristics. Here, when we apply the gate source voltage, we can see that the current increases non-abruptly. So the similar performance can be seen by the output characteristics. So by this 3-terminal transistors, we can have fine-tuning the channel conductance with additional control terminal called gate, and also we can decouple the reading and writing operations. So the hypothesis which we had here is, in a 3-terminal transistors, we can have optoelectronic modulation, which will be able to obtain the continuous conductance states, conductance with stable states. So the approach which we took is the 3-terminal transistors with a photosensitizer. If we can have a photosensitizer, then it aids in achieving the optical and electrical modulation simultaneously. So for that, we had a material called cesium lead bromide perovskite nanocrystals. So it can act as a light absorbers, and also it can have a size tuning band gap property. But however, this cesium lead bromide itself cannot act as a semiconducting channel because it is not a good charge transport. It does not have a good charge transport property. So for that, we can have one more material and make the semiconducting channel as a hybrid channel, which will aid to have a better charge transport and be able to have a linear synaptic functions. So the material which we had is indium gallium zinc oxide. So together with indium gallium zinc oxide and cesium lead bromide, we will be able to have a optoelectronic modulation to achieve the stable conducting states. So if we compare the biological synapse with the artificial synapse, we can see that the presynaptic input can be applied to the gate terminal, and the postsynaptic output can be collected from the source drain terminal. So if we see the thin film transistor characteristics, we can see that upon light illumination, the transistor turns on earlier because it has more carriers upon light injection from the cesium lead bromide to the indium gallium zinc oxide. So the similar performance can be seen from the output characteristics. So the increase of current during light illumination confirms the presence of photogating effect. Also, whenever there is any information processing in the human brain, it goes to the sensory memory, and without any attention, it forgets. However, with attention, it stores in the short-term memory, and the forgetting time is from milliseconds to seconds. And with continuous rehearsals, we can convert the short-term memory to long-term memory by varying the pulse with the number of pulses or light intensity. So for electrical characterization, we will also be able to do the short-term memory and long-term memory by applying the voltage spikes. If the voltage, when applying the voltage spike, the current retention decays faster, which confirms the presence of short-term plasticity. However, if the retention is longer, then we can say that the device has long-term memory effects. So we can able to do similar programming in our device, and we can see that by applying the 2 pulses, which is called as pad pulse facilitation, we can see that the second spike is higher than the first spike, which means that the number of charge carriers are not able to goes back to its baseline current because the time difference between the 2 spikes are close enough. So this kind of temporal activity dependent spiking plasticity, and also it confirms the presence of short-term memory in the device. However, when we increase the number of pulses, the electrical pulses, we can also see that there is no long-term memory because the baseline current and the retention are not available. However, if we give the negative voltage, we can see that the retention is there, and which confirms the presence of non-volatile memory because of charge taps between the semiconductor insulating channel. And when we study the device with just optical programming, we can see that the retention is more slower, and also because of the persistent photoconductivity effect, we can able to have the long-term memory effect by using optical programming. Also, because of the type 2 band bending, we can have more charge carriers, and the slower retention is because of this extra carriers transferred from the cesium lead bromide to the indium gallium zinc oxide. Also, we can do the memory consolidation by varying the pulse intensity or pulse with the number of pulses, and then we can have a more controlled modulatable programmable states by using the optical programming. Also, we need to have a programming and erasing functions happening at the same time in the device. For that, we will have a photonic potentiation and electrical depression. Both are long-term, both are having the long-term plasticity effect. So for that, we will have 20 optical spikes, which helps to increase the channel conductance. And then we will have 20 electrical spikes, which helps to decrease the channel conductance. And then we repeat it to see the endurance and the device programmability and stable states. Also, there is a phenomenon called associative learning, which basically has, which is also called as Powerless Dog Conditioning, which means that the dog, before conditioning, the dog is given food and then it salivates, and then when we ring the bell, the dog doesn't salivate. This is the normal procedure before conditioning. However, during conditioning, we ring the bell and then we give the food and the dog salivates. So we continue this persistent training, and then after the training, we can see that with just ringing the bell, the dog salivates. So the basic concept of this associative learning is the weak stimulus will be strengthened by associating it with a strong stimulus. So we can implement a similar learning rule in our device, where the bell is considered as the electrical stimulus and the food is considered as the optical stimulus. So by ringing the bell, the current level is below the threshold, and by giving the optical spikes, we can see that the current is above the threshold. So by simultaneously training with bell and food, which means optical and electrical spikes, we can see that the current level is above the threshold. However, this phenomenon goes back, so the forgetting takes place, and after 30 minutes, it again goes back to the its own state, which means which is below the threshold. So for retraining, we will only need a limited number of spikes, and then we can able to have a associative learning with just limited number of training. So through our study, we have seen that the optical approaches have certain advantages in our system, and electrical approaches have certain advantages. However, using optoelectronic approach, we will be able to emulate all the basic synaptic functions using the hybrid TFT, hybrid channel TFT. Yeah, that's all. I'd like to thank and acknowledge Prof. Nirpan and my colleagues. Thank you.
Thank you. Now the talk is open for a few questions.
Can you comment on your fabrication technique? How did you make your film? What kind of?
Sure, Prof. So the basically we have silicon dioxide substrate, and then we have source drain electrode, and then indium gallium zinc oxide using sputtering, DC sputtering and RF sputtering. After that, we spin coated the cesium lead bromide as the photosensitizer, and finally we have a PMMA as the encapsulation, and yeah, and that's all.
Okay, thank you.
I have one question.
Yeah.
Lakshmi.
Yeah.
So you are using kind of insulator, then you have a conductive bridge, right, between the two electrodes.
Yeah.
So commonly used is titanium oxides or MgO, isn't it? The insulator. What is now the state of art insulator people are using as bridge?
So the insulator which I am using is just silicon dioxide. I
Silicon
think it's like
dioxide.
100 nanometer silicon dioxide, yeah. Which is
Okay.
like, yeah.
Because the idea is very good, but I am worried about the,
Mhm.
the cycle of writing and reading, You use many pulses, then there is kind of material fatigue, then you might have some kind of drawback in the performance of the material.
You mean with respect to the perovskite nanocrystals you are saying, is it? Or the
Yes. I mean, the bridge between the
Mhm.
two electrodes, then I think there will be some failure if you use the mini cycles.
Yeah. But one thing
concerns.
which we tried doing the repeatability test is that we did not see, for 10 cycles, we did not see so much variations, but yeah, for many cycles, probably.
Oh, yeah, but this is limited number. But I think for you is no worry because this is just a proof of concept. So
Yeah.
you are not yet at the industrial stage. Okay,
True. Yeah.
thank you. So if any more question? If no more question, then thank you, Sir Kashmi. So we move to the next speaker. Thank you. Next speaker is Neha Garg from IIT Delhi in India. And the talk is about Kuramoto model-based data classification using synchronization dynamics for spin-hole nano oscillator. So you can start, Neha. You have 12 minutes. Neha,
Yeah, hello.
are you ready?
Yes.
Okay.
So, greetings everyone. The topic of my presentation is Kuramoto model-based data classification using the synchronization dynamics of uniform mode spin-hole nano oscillators. So, firstly, I'll tell you briefly about the application of Spintronic devices-based neuromorphic computing. Then I'll go deep into my topic. So here are a few examples of applications of Spintronic devices. We can see that if instead of conventional memory, we use MTJ-based memory, Spintronic device-based memory, then area of chip reduces by 30 times. Or in the recent scenario, there is a huge speed gap between memories, but that gap can be filled if we use Spintronic devices-based memories. And further, our devices can be speedified with the help of non-volatile logic circuits. So in the recent generation, there is no doubt that we are using centralized computing, but still that is having a lot of issues. For example, difficulty in adaptability, real-time processing means there is a huge lag between input and output, and that's not required. So in the near future, with the help of distributed IT systems plus centralized processing, we will be at a better level. Then system will be autonomous, means self-sustained, and real-time processing can be enabled that way. And briefly talking about neural network, we can simply say that this is just a mapping of inputs to outputs with the help of some function, and calculation of this function is critical. This is done with the help of some modeling and algorithms. Or in a more specific way, we can see that a neural network consists of an input nodes. Then there are some weights. So this can be some array multiplied with weights. We will get some outputs, Z1, Z2, and Z, and so on. Then some activation function is applied to get final outputs Y1, Y2, dash, 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 Ym. So broadly talking about neural network, we can see that this has two components. Synapse in biological language, synapse, and that is memory, and neuron, that is computation. So memory and computation are the main building blocks of a neural network. So in a conventional implementation of AI, memory and computation used to take place on different devices. Because of that, there was huge shuffling of data, and a lot of energy and time is consumed in this process. But in the unconventional implementation of AI, people have already started working on crossbar array type of structures, where these nodes are nothing but synapses, work as memory element, and computation is also done. So here, memory and computation takes place at the same hardware level. So these nodes can be anything, like these can be transistors or spintronic devices. But why we are interested in spintronic devices? Because of the following benefits: highly dense, dynamical nature. Obviously, we need lower power consumption. Operability should be at room temperature, long life, non-linearity, and no doubt on-chip computation means training can be done at hardware level, and that is necessary here. But point here is, what if these nodes are interacting? So if people have already started have been working on domain wall based devices, but if we use oscillators, Spintronic oscillators in these nodes, so then we can see that how problem will be simplified. So here we can see that with the help of multi-layer perceptron model, if we are just having 12 inputs, so circuitry is so much, it's huge. So there are so many interconnects. Each interconnect basically represent one weight, and that requires separate device to store. So if instead of this, we utilize the synchronization dynamics of oscillators, we will land with a very simpler circuitry. And how this I'll explain later on in detail with the help of synchronization dynamics of oscillators. So this is something which is done with the help of oscillators, and then number of trained parameters reduces to a large extent using oscillator based neuromorphic computing. So here what these people have done, these have used 4 output oscillators, and A and B are the input oscillators. Using this 6 oscillator network, they have generated a synchronization map, and with the help of Kuramoto model, which is a mathematical model. And then they have carried out binary classification. So one benefit of this approach is that here number of classes that can be classified varies logarithmically. So here if we are having 4 output oscillators, so number of classes can be classified to raised by 3, means 8 classes can be classified. So but the main thing is to apply this approach, Kuramoto model based approach, to variety of Spintronic oscillators. We need to first verify whether this approach can be applied to Spintronic oscillators, and more specifically on uniform mode spin hole nano oscillators. So in that direction only. So I can firstly explain briefly what is Kuramoto model. So this is given by a simple basic equation where instantaneous frequency of oscillator is represented by the natural frequency with some amplitudes, factors, and coupling strengths. This is the main important factor here, and sign of the dephasing between the oscillator. So first of all, I have studied Kuramoto model for 2 oscillator system. Here what we have done, the frequency of oscillator 1 is kept fixed for particular value of coupling constants. We can see that this is something we are getting. So oscillators get locked for a particular range of frequency, and this is nothing but the synchronization range. In this synchronization range, oscillators will have same frequency, and outside this they will just follow their natural frequency. So the same procedure is then carried out for different value of coupling constants, and then finally we get the relationship between synchronization range and coupling constant that is used in Kuramoto model. So as I said that we have to verify whether this can be applied to SHNOs too. So for the same purpose, micromagnetic simulations are also carried out. These snapshots just verify that our oscillators are oscillating in uniform mode, just completing one complete rotation of 360 degree. So here FFTs are calculated to find frequencies, the same procedure. If frequencies are same, we say that oscillators are synchronized, otherwise not. So in micromagnetic simulations also, we have got the similar relation, but here we have got the relation between synchronization range and distance between SHNOs. If you remember earlier from Kuramoto model, we had got a relation between synchronization range and coupling constant that is used in Kuramoto model. So indirectly, I can say that we have got a relation between the coupling constant and distance value between SHNOs. So this is of benefit because ultimately we cannot do any kind of classification with the help of 2 oscillator model. So for oscillator synchronization dynamics is studied further. So this is a geometry taken for that. In micromagnetic simulation, here we can see that for each value of distance between oscillators, from those 2 plots we have calculated the corresponding value of coupling coefficients in Kuramoto model, which is needed to be used here also. So using this correlation, we can see that this synchronization map that is generated using both Kuramoto model and micromagnetic simulation matches fairly, and which is something we wanted. So then this synchronization map generated is used to classify binary data with the help of this algorithm. So briefly telling, first of all, we have firstly inputs in n-dimensional space that is firstly reduced into 2-dimensionality with the help of some reduction technique, And then synchronization dynamics of the system is studied. And one of the category will lie in synchronization region and other will in desync region. And this way we will be able to classify data. So here Fisher Iris data set is classified using 3 binary combinations of that. Here we can see that Setosa is very easily classified from Virginica and Versicolor using the previously generated sync map, but issue is with Versicolor and Virginica. So for that, this sync map is moved such that we have just changed the value of F1 and F2 such that our sync map will cover most of the Versicolor points, and these will lie in sync region and Virginica will lie in desync region. So with this methodology, we have obtained quite high accuracies. If I briefly summarize my work, first of all, I have studied synchronization between 2 oscillators using both Kuramoto model and micromagnetic simulation. And ultimate goal was to get a relation between the distance value, which is to be used in micromagnetic simulation, with the coupling constant value in Kuramoto model. And using that information, synchronization map is generated for 2 input, 2 output oscillators with the help of both 2 models. And then we have generated synchronized just classified binary data classification we have carried out with the generated synchronization map. Last but not the least, I would like to thank my professor Devanjan Bhaumik and PK Murthy for always supporting me and guiding me. Thank you so much.
Thank you, Neha. So now it's time for a couple of questions.
Yeah, sure.
Neha, what's your novelty? Is it the introduction of the Kuramoto model, or what is your novelty? What is the thing that you introduced?
Yeah, basically I said that with the help of Kuramoto model, data classification schemes have become much easier. Means we can use lesser number of parameters to train our network. So if this Kuramoto model can be applied to our uniform mode SHNOS2, means Spintronic nano oscillator 2, so then we can just carry out all the classification and training at Kuramoto model only. So, or we can also say that this is a proof of concept that Kuramoto model can be applied there, and we have carried out classification also with the help of that.
Okay, thank you.
Okay, any more question? Okay. So I can take chance and ask one question, Neha.
Yes, sure.
What is different from normal oscillators? There are some group in France, they are using only single oscillator. I believe when you are using 4 and maybe you want to use even more, things become more complicated to synchronize all of them. So it becomes challenging. So what is the difference between the synchronized oscillator and single oscillator?
Yeah, in using synchronization dynamics, as I already told in that slide, that number of parameters have reduced so much. That was all because of the synchronization dynamics only, because I understand that there are 4 oscillators, but ultimately using the help of synchronization dynamics, we will be having 8 regions. So with 4 oscillators, we can classify finally with two inputs, obviously, we can classify more number of classes, not that equivalent. And I understand that people are also working on 1 oscillator system.
Yeah.
That is something like reservoir computing, and they are just emulating the network with the help of 1 oscillator. That I understand in some different, that is some in some different aspect, and I'll also look into that. But
because from a technology point of view, it is very challenging to synchronize 4, an oscillator. People are struggling to synchronize only 2. But if you can use just the different voltage values and you can have different frequencies, then could be, easier. But I think it's interesting to try. Yeah. I think what we are talking about today maybe will not be valid in 5-10 years. Technology go very fast, so surprise us all the time. Yeah.
Absolutely.
Okay, so if no more question, then
can I
take the speaker again. Sorry?
Can I ask? I have raised my hand.
Oh, sure. Yeah, please, go ahead.
Yeah, just a comment first. Yeah, I think what you were saying that synchronizing oscillator is a challenge. The day before yesterday, or was it yesterday? This Professor Johan Ackerman.
Yes, Ackerman, yes.
Yeah,
yes.
he showed even 8 oscillators being synchronized.
Yes, I agree with you. I agree with you.
Yeah.
That's what I said. What we are thinking today maybe is no more, true after a few years. Technology can go fast, but actually, just I want to understand the difference between single oscillator, which still can give us different frequencies, and maybe you have more. Then that's I mean, I agree with you. So we can make for in
I have
a couple of years.
Can I make a comment, because I was the supervisor for this work regarding the single oscillator thing?
Yes.
Oh, Devanjan, can I ask a question first to Neha? Maybe you can answer that.
Sure.
Yeah. Of course, my understanding is just based on the talk that I've attended. I just wanted to ask over here, Neha, when you're talking about these 4 oscillators, and of course, yours is a simulation based, unlike the results that were shown the other day, which were experimental results. Yeah. So is this configuration is different from what he was showing over there? They had a constriction based, a region where when we drive the current at particular specific currents, they were able to, they were able to sustain the oscillation as well as able to synchronize them within certain range. So how do you, make your, in this simulation, what way it is done? I mean, you have like MTJ configuration, or is it like, again, a constriction kind of a configuration? Because the 2-dimensional array, which he was showing, similar to like the 4 you have shown, was probably, I don't know how it is simulated. I mean, in the numerical scheme, in the simulation scheme.
Yeah, I understand. Professor John Ackerman is basically working on nanoconstriction geometry, and here we have used nanopillar based geometry.
Oh, nanopillar based. All right. Yes. So here the current is transfers to this.
Yeah, right.
Over there they have a PYPT layer where he's driving the current in plane through the PT layer, and in your case, yours is a nanopillar like an MTJ configuration, and then you drive it perpendicular to this. Is it like what you are trying to say?
Yes, right. Sir.
Okay, got it. Thank you. Yeah, Debanjan, please go ahead with your comment. Yeah.
Thank you, Neha. Yeah, so I think we can move now to the next speaker. Next talk will be presented by Chan Jianping from NTU, Singapore. And the title of the presentation is Deterministic Domain Wall Motion with Synthetic Antiferromagnetic Pin Insights for Synaptic Applications. Jianping? Okay, I can see your slides. Okay, please go ahead. Yeah.
All right. Hi. Good evening, everyone. My name is Jianping, and I'm a PhD student from Nanyang Technological University under the Department of Physics and Applied Physics. I would like to first thank the organizing committee for allowing me the opportunity to present a simulation study, and the purpose of which is to demonstrate pinning of domain walls using synthetic antiferromagnetic coupling. So following in line with the theme of this event, our motivation for this project also comes from the change in the perspective of modern computing, and specifically the introduction of neuromorphic computing, which is thought to consume significantly less power than compared to our present von Neumann architecture. And for this presentation on domain wall pinning, we are focusing on the synapses, which are the so-called memory units in your neuromorphic computing. And in particular, we are studying an alternative way in which we could generate several resistive states using this concept of domain wall pinning. So a very well-known and energy-efficient method of achieving a synapse which possesses multiple resistance states is to create a domain wall device that is composed of magnetic tunnel junctions. The resistance of these MTJs depends on the magnetic states of the free layer, which can be controlled by domain wall motions using different kinds of spin torques. In our simulation, we are using spin orbit torque to drive the domain walls. And since the domain wall motions behave in a stochastic manner, so pinning the positions of these domain walls deterministically becomes a central focus of a synapse with multiple resistance states. So, and our main idea is to essentially replace a single free FM layer with two ferromagnetically coupled layers with pinning sites that are synthetically antiferromagnetic. The premise of our concept is based on the difference in the energy levels between the soft regions and the ferromagnetically coupled regions, which then forms an energy barrier as the domain wall travels across the FM layer and gets pinned along the antiferromagnetic pinning sites as a consequence of such an energy barrier. And our material of spin orbit torque coupling, high spin orbit coupling would be two heavy metals of an opposite DMI, so that the resulting domain walls in both layers have the same chirality to enable smooth domain wall motion. Then you see in this video, we show a first demonstration of pinning a domain wall using synthetic antiferromagnetic sites to pin a reverse down domain from the left here. So in the top diagram, we observe that the domain wall on the left is unable to depin with current that is below a certain threshold, since it does not have sufficient energy to overcome this soft pinning site. Instead, we find only a damping oscillation of the left domain wall with no depinning happening across the pinning site. And in contrast with the depinning current, as in this bottom diagram here, the domain wall is able to depin and moves across the pinning site and then interact with the domain wall from the opposite end of the pinning site. You can see here. We also observed that for depinning to take place, both domain walls have to realign themselves before exiting the soft region and move off with domain wall magnetization along the direction of spin accumulation. And during our simulation, one interesting thing to note about the domain wall configurations at the soft pinning site is that depending on the length of and the inter-exchange coupling between the pinning site, we generally find two types of domain wall configurations at the soft pinning site. If the pinning site has a larger length or large interlayer exchange coupling, the soft configuration is quite distinct, and we observe two down to up domain walls on the left and right of the pinning sites as a result of DMI. And for the case of a shorter pinning sites and low interlayer exchange coupling, we come across an antiferromagnetic domain wall in the soft region with ferromagnetic domain configurations which are continuous with the domains in the FM region. One of our purpose, apart from demonstrating domain wall pinning, is to explore some relationships between several parameters, including the interlayer exchange coupling, the DMI, and as well as the length of the pinning sites with respect to the depinning current. If we take a look at the depinning current when the length of the pinning sites is large, the depinning current becomes a constant, and this constant increases proportionally with the interlayer exchange coupling. Here, taking some large interlayer exchange coupling and then fixing the current that I'm applying, and as well as the DMI, we show the case of two different lengths of pinning site. So for a shorter pinning sites, the oscillations from the domain walls at both ends are enough to allow both domain walls to interact in the middle of the and depin from the pinning site. However, at larger lengths, the same oscillations now do not span enough for both domain walls to interact. So you will need a larger current to increase the oscillations to depin as the length increases. And then at even larger lengths, the depinning current should then remain a constant, since the magnitude of the energy barrier is the same irrespective of the length of the pinning site. Now, by varying only the DMI, we observe that a larger depinning current is required as the DMI increases. So as you can see here in the second diagram. And this happens because a larger DMI reduces the oscillations from the domain wall at the right end of this pinning site as it experiences a higher DMI field. So a larger current is then required to maintain the same oscillations as previously in the first diagram in order for the domain wall to deplete. And previously, I have mentioned about domain wall configuration at the pinning site with smaller lengths and low interexchange coupling, and how the relationship between the deepening current and the DMI may be different. So here we find decreasing deepening current, okay, with an increase in DMI, which is opposite of what we expect from the previous slide, because here we have a different configuration. And if you take a look now at the domain wall configuration at the top layer, the domain wall is now pointing in the opposite direction to the DMI field. And this domain wall is, so increasing the DMI will thus increase the contribution of the DMI top, which then drives the domain wall magnetization towards the y-axis in exchange for a smaller deepening current. And finally, to demonstrate the multiple resistance states of such a synapse, we have embedded 5 pinning sites and apply 4 pinning or deepening currents, as shown in this graph of domain wall position against time. For current that is below a threshold current, okay, we see that the domain wall remains pinned at the SAF pinning site, regardless of the number of current pulses until a certain threshold current. In this case here, a current of 5 times 10 to the power of 11 amperes per square meter is applied. And so in summary, we have successfully demonstrated the use of SAF pinning sites to pin domain walls driven along a FM coupled regions using the energy barrier as a result of the opposite signs of the inter-exchange couplings between the SAF and the FM coupled regions. We find also that the pinning current is proportional to the SAF inter-exchange coupling for large pinning sites lengths. And for the case of shorter pinning sites, the pinning current reduces with shorter pinning sites, and its relationships with DMI would depend on the type of domain wall configuration of the pinning site. And of course, as a minor disclaimer, this is merely a simulation study. So in the future, we will also need to be able to reproduce such a phenomenon in an experimental setting. And with that, I thank the audience for your kind attention, and that's the end of my presentation. Thank you very much.
Okay, thank you, Jean-Pierre. So now it's time for questions. Any question? Jean-Pierre, I have a short question. How do you create this region? I mean, do you have some idea how to make them?
So based on our studies, we were thinking that if we were to produce a soft layer and then apply some annealing along the regions which we would like to have FM coupling. So in theory, that should alter the properties, and this is what we would be intending to do as our first step to create such devices.
Okay, using annealing, but
Yes,
locally,
correct.
right? Locally.
No.
In the whole film or locally?
Sorry?
In small region of the nanowire or along the whole nanowire?
Okay, so in this case, we are applying along the regions of, let me go and let me change. Yeah, so we intend to anneal along the FM coupled regions that we want to. So this one is the one that we leave.
Yeah, but I think you will also create a kind of change of the properties in the whole device, not only in specific region. So possibly you might use some, I think you have to do it locally, very in nanoscale.
Yes, we are also exploring doing it in the reverse direction. So instead of having FM wires and south as the pinning side, we could do it the other way around. So if you do it the other way around, perhaps that may answer your question, but we have not done any simulation studies on such
this is a theoretical study. I understand.
Yes, correct.
Okay.
Correct.
Okay. Thank you.
I had a couple of questions. Just one question, maybe. Hello, this is Debanjan.
Yeah, yes. Please go ahead. Yes.
Yeah. So my question is that on what basis have you chosen the length of the pinning side and the distance between two alternate pinning sides or two consecutive pinning sides? Like here you have an L and you have a 100 nanometer, right? What is the basis for choosing this L and this 100 nanometer?
Okay, so for the case of neuromorphic computing, okay, we are intending to create multiple resistance states such that each state would be quite small. So we were thinking about 100 nanometers would be a good starting point to.
No, but can you, are these pinning sites under your control or not? I mean, if they're not under your control, you cannot really have them at this kind of distance, whatever you want, right?
Okay, right. So that's the reason why I'm saying that based on this simulation studies, we find that with this particular 100 nanometers, it seems to be able to work. Okay, but as a disclaimer, we have not been able to we have not started doing some experimental studies on this yet.
No, is it even possible to put pinning sites at specific locations? I mean, I don't know. That's why I'm asking. So something must be guiding your simulation, right? Anyway.
This is simulation. I mean, theoretical study. I think.
Yeah, we can discuss this later.
Maybe experimental work can be challenging, but possible.
Yeah.
I think.
Yeah.
Possible.
Okay. Thanks. Yeah. Thank
you very much.
Thank you. Yeah.
For the questions.
Thank you, Jean-Pin. So now we move to the next speaker. So next talk will be given by Tokyo Chin from Tohoku University in Japan. And he will be talking about binary neural networks based on CMOS invertible logic. So Chin, are you ready? I can see you. Yes. Okay. Can you enlarge the screen, please?
Is it okay?
Yeah, I think it is small. Can you increase more?
Go to the display settings and change it to duplicate.
Sorry. Oh.
So it is in the setting, isn't it? Okay. Now it's good. Now it's yes.
So thank you for introducing. I'm Tokyo Shin from Tohoku University, Japan. Today I will talk about energy efficient training hardware for binary neural networks based on CMOS invertible logic. And I'm sorry about title. I forgot my title when I saw the abstract. So let's start. Let's begin. So advance of deep neural networks leads to the explosive growth of AI applications such as image processing and speech cognition. So also, neural networks are widely used in IoTs. Generally, these neural network applications are cloud-based. Impulse can be computed on edge devices which have limited resources. However, training requires massive training data and high computation power. So training is computed on the server, which consumes large amount of energy. So in order to realize fully edge-based neural networks, the energy-efficient hardware for training neural networks is required. The training algorithm of neural networks is well-known backpropagation. Backpropagation updates parameters of neural networks such as weights using backpropagated error. For maintaining high cognition accuracy, backpropagation requires high precision floating point computation. Even inference can get computed by binary. So it makes hard to implement energy efficient training hardware. So our goal is energy efficient training hardware using hardware friendly training process without backpropagation. Using this training hardware, we can handle training and inference on the same edge device. The proposed hardware trains the parameter of neural networks through probabilistic bidirectional operation based on CMOS invertible logic. Inference process converted into an energy-based model, Hamiltonian, whose global minimum is corresponding to the correct state of parameters. Next I introduce the CMOS invertible logic. In CMOS invertible logic, the desired function is converted to the Hamiltonian, which means an energy of network based on Boltzmann machine. For example, the two-input invertible AND gate is represented as this network, which has two input nodes and an output node. Each node has a bias H, and they are connected each other using weight J. And each node operates stochastically, and node operations are given by these two equations. When the invertible AND gate is operating at backward mode, the MC mode node, which is the output node, is fixed. For example, M3 is fixed as 0, M1 and M2, these are input nodes, are stochastically converted to valid state for AND gate, such as 0 and 0, or 1 and 0, or 0 and 1. The Hamiltonian must be designed so that all nodes are in the valid state for the desired function when the Hamiltonian is global minimum. This is an example of the Hamiltonian for two-input invertible AND gate. First, this table shows every combination which can be represented by 3 nodes. In this table, the valid state for AND gate are these 4 states. And then H and J are calculated by linear programming that makes the minimum energy at these 4 states. The basic logic functions such as AND or exclusive OR can be obtained by linear programming. The node in the network operates probabilistic computation. This probabilistic computation can be realized by MTJ device model, or it can be approximated by stochastic computing. The approximated node operations are given by these 2 equations. In stochastic computing, hyperbolic tangent function is approximated as stochastic hyperbolic tangent, which is calculated using a finite state machine. And this finite state machine can be easily implemented using a saturated up-down counter. In CMOS invertible logic, the probabilistic node is realized using this spin gate circuit, which is designed using CMOS. So CMOS invertible logic can be used for a large circuit like a multiplier or training hardware. The proposed hardware is based on CMOS invertible logic. So inference of neural networks is converted to the Hamiltonian, and proper parameter of neural networks are calculated by backward operation without backpropagation. But only a function which can be represented by combination logic can be converted to the Hamiltonian. But convolution function is the most important function in the neural network, the convolution function, is represented by sequential logic. So in order to convert inference to the Hamiltonian, we transform the convolution function to matrix multiplication. The matrix multiplication can be represented by combinational logic. Therefore, we can convert inference to the Hamiltonian. However, the entire computation of inference is too complicated to directly convert to the Hamiltonian by linear programming. So first, matrix multiplication is divided into small components which are composed by basic logic gates. For example, the convolution in binarized neural networks can be computed by exclusive NOR gate and a bit counter. And then the large Hamiltonian, in this case for training hardware, is made up by merging this small Hamiltonian from the components. The obtained Hamiltonian looks like this figure. It contains input node for trained data and a label node for true label, weight node which represent the weight of neural network, and arbitrary nodes. When the proposed hardware operates, the input nodes and label nodes are fixed by given trained data and true label. Then arbitrary node and weight node are blockaded by noise signal, and eventually every node are converted to the valid state for given data. The hardware performs backward operation corresponding to the given one data. So weight nodes are settled down for optimal states to train data. However, this obtained state is optimal only for the given one data, not for the entire data set. So the final weights for neural networks, large W, are means of individual small weights, which are obtained from individual trained data. With this training process, using backward operation of CMOS invertible logic, the proposed hardware can train the neural networks without backpropagation. And next is an evaluation of the proposed hardware. For performance evaluation, we implement a training hardware for two-layer binarized neural network model and train this model with modified MNIST dataset. The trained model contains two binarized convolutional layers. Filter size of each layer is 5 by 5 pixels, and C1 layer has a one filter, C2 layer has a 3 filter without biases. And then the dataset used for training is modified MNIST dataset. We use only images of 0, 1, and 5 from the MNIST dataset, and the size of images is downscaled to 9 by 9 pixels, and all images are binarized. And the trained data, the number of trained data is 10,800, and test data is 3,600 data. The proposed hardware is implemented on FPGA. The FPGA board we used is Digilent Genesis 2, powered by Xilinx Kintex 7, and its clock frequency is 12.5 MHz. The hardware receives trained data and label from the PC through UART interface and send the trained weight to the PC. And resource utilization of the FPGA is shown in this table, and the training hardware for two-layer BNN model, as I mentioned before, has a 2,645 nodes. Then we compare accuracy of proposed hardware with conventional training using backpropagation on a CPU. First graph is accuracy versus training latency graph, and second one is accuracy versus the number of trained data graph. The proposed hardware achieves 87.97% accuracy at 67 milliseconds, but the conventional training achieves equivalent accuracy at 1.3 seconds. Also, the proposed hardware only trains 100 data, but it achieves best accuracy. However, the conventional training requires much more trained data in order to achieve high training accuracy. And this table is performance comparison of the proposed hardware with conventional training on the CPU. The best accuracy of the conventional training is a little bit higher than this work. However, the training latency of the proposed hardware is much more faster than conventional. Also, the power consumption of the proposed hardware is only 913 milliwatts. It is approximately 134 times higher energy efficiency than the CPU. So, and this is a final summary. In this work, we introduced energy efficient training hardware based on CMOS invertible logic. And the proposed hardware was implemented on an FPGA and trained two-layer BNN model. It achieved significant reduction in training latency and power consumption. And our work is just not suitable for the larger neural network model which are used in actual application, but we hope that our work will contribute to the advance of the fully edge-based neural networks. Thank you for your attention.
Thank you, Shin. So now it's time for a few questions.
Yep, let me ask questions.
Yeah, please go ahead. Yeah.
So even the number of training is 100, let's say your accuracy is quite good. Have you tried to increase the number of trained data, let's say up to 500 or 1,000 in your system?
Yes, we tried much more training, but actually it quite below the noise parameter is this with this our proposed hardware needs noise signal for the training, but this noise is controlled by several parameters, but the data set, the amount of data is affect this noise. So if we train more data set, and we need to find the noise parameters.
I see.
Yes.
Okay, thank you.
Okay, any more question? Sheen, I am very curious. I'm not expert in neural network, but if you use this device for, let's say, new memory, like a spin torque type memory, it can work also?
Maybe yes, maybe it can work good. I don't know well.
Okay, so if you, because I think this is just about the interface, right, between the real memory. So the question is, if you use instead of CMOS, you use let's say phase change memory or spin torque type, if this kind of work can be useful for, I mean, it's a question that maybe you might think about it in the future, then you can have much more collaboration with the memory guys.
Yes. Thank you.
Okay. Any more question? Then if no more question, we can move to the last speaker. Thank you, Sheen.
Thank you.
The last speaker is Monalisha from IICS Bengaluru in India. So it will be on emulation of synaptic plasticity in permalloy, isn't it? Permalloy-based artificial synapse for neuromorphic computing. Okay, now we can start, Monalisha. It's good. I think the full screen can be seen. Yes, you have 12 minutes.
Okay. Should I start now?
Yes, please, Monalisha, you can start now.
Okay. Good afternoon. The title of my talk is Emulation of Synaptic Plasticity in Permalloy-based Synaptic Artificial Synapse for Neuromorphic Computing. The contents goes like this. First, I will give a brief introduction about neuromorphic computing and human brain. Then I will speak about my main work based on permalloy-based synaptic transistor, and finally, I will give a brief conclusion. The digital computers we use in our day-to-day life are based on von Neumann architecture. This von Neumann architecture is characterized by a separately placed memory unit and processing unit. As they are separately placed, the data transmission limits the speed of the device and the scalability. On the top, the separation, due to the separation, it consumes a lot of additional energy. And the problem it arises called von Neumann bottleneck. As you know, the current generation is the generation of artificial intelligence and the Internet of Things, where there is explosion of huge and complex data sets, and definitely this current computing paradigm is inefficient while handling this problem. So what's next? The scientists has come up with a solution as a different computing paradigm called neuromorphic computing. So I will give a brief introduction about neuromorphic computing. So in neuromorphic computing, we basically emulate the functions and information processing of biological nervous system. So as it copies the human brain, the computing paradigm has highly parallelism and it is fault tolerant like the human brain. On the top, it is adaptive to the environmental changes. And very importantly, it has the combined processing and memory unit. So we can say it is a direct solution to the von Neumann bottleneck problem, as I discussed before. So the human brain. The human brain, the biological computer, consists of neurons and synapses, which are called as the computing unit. In this talk, we'll be mostly focusing on synapse. So what is a synapse? A synapse is a functional connection between neurons. So what it does is it allows the passage of electrical as well as chemical signals from one neuron to another neuron. And the synapse has the beautiful property that it can store and process the information simultaneously. In this talk, we mostly focus on emulating the synaptic functionalities in electronic devices. So we have chosen electrolyte gated transistor. So one EGT has the same structure as a conventional field effect transistor. The only difference is that the gate dielectric is replaced by an electrolyte. So during gating, the ions get segregated and it forms an electrical double layer at the channel electrolyte interface. And this acts as a nano capacitor, producing a huge electric field due to the huge capacitance. And this gives fantastic outcome while using one EGT. And additionally, it also involves electrochemical doping that giving rise to non-volatile change of channel. Now we will move to the main work, which is formula-based synaptic transistor. So that is basically one electrolyte gated transistor where we have used 3 nanometer of formulae as the channel and an ionic liquid as the gate dielectric. The transfer curve resulted in a big hysteresis loop, and this hysteric behavior says the non-volatile and reversible change of channel conductance. And that is a signature that the device is suitable for emulation of synaptic properties. By sweeping the gate voltage rate, we could obtain one highest conductance modulation of 11% at room temperature, which is one of the highest among metals. Multi-level non-volatile conductance states are crucial for analog computing. And in this artificial synapse, we have realized it by applying gate pulses of different amplitudes. We have also separately checked the retention, which is showing very good retention for the separate states. Before emulating the synaptic functions, I would like to give a brief analogy of the biological synapse and our synaptic transistor. So as I discussed, one synapse is a functional connection between two neurons. So the signal transmission starts by firing of an external stimuli, and that results to flow of neurotransmitter, and it results a potential drop in the postsynaptic neuron. So here the external stimuli is applied by the gate voltage. The mobile ions in the electrolyte act as the neurotransmitter. And finally, the potential drop, we see it as the channel conductance that represent the synaptic weight. Synaptic plasticity is the beautiful property of synapse. It means that the synapse has the ability that it can change its weight depending on the activity. And this synaptic plasticity is the basis for learning and memory in human brain. Coming to short-term plasticity. This is responsible for the computations, working memory, and short-term memory in the human brain. We have emulated several functions called excitatory postsynaptic conductance and paired pulse facilitation in the synaptic device successfully, which is very much like the biological brain. So the EPSC was emulated by firing a single gate pulse, while paired pulse facilitation was emulated by firing 2 gate pulses. We could also show this synaptic plasticity can be tuned by tuning the gate pulse amplitude. Here we can see that the synaptic weight is changing as a function of gate pulse amplitude for both positive and negative gate polarity. We have also shown the conductance, the synaptic weight can be tuned by changing the gate pulse duration in both positive and negative gate polarity. Lastly, we emulated long-term plasticity. So long-term plasticity is considered to underpin learning and memory in the human brain, which is very important. Here we have emulated long-term potentiation and long-term depression function, and also emulated cycles of the potentiation and depression, showing good repeatability of our device. Now, the human memory system. According to multi-store model, the human memory system consists of short-term memory unit and long-term memory unit. And the data can be transferred from a short-term memory to long-term memory by rehearsal or by repeating the event. And we could successfully experimentally demonstrate that by firing a number of pulses. By increasing the number of pulses or by repeating the activity, we could successfully show a transition from a short-term memory to long-term memory. At the end, we also showed that our device can do sort of processing as well. The Powerless synaptic transistor can act as a high-pass filter using the short-term facilitation phenomenon. To demonstrate that, we have applied series of gate pulses of different frequency, and we see that the amplitude gain is increasing as a function of frequency, showing high-pass filtering behavior. So as a conclusion of Powerless synaptic transistor, in the synaptic device, we realized a highest conductance modulation of 11% at room temperature, which is one of the highest among metals. We realized multi-level non-volatile conductance states, which is very crucial for analog computing. In the device, we emulated synaptic functions demonstrating short-term and long-term plasticity. And very interestingly, we showed the human memory system in the artificial synapse. And finally, the high-pass filtering behavior is demonstrated. So in a final conclusion, we achieved learning, memory, and processing in a single synaptic device. So thank you all for the attention.
Thank you, Mona Lisa. So now it's the work is open for questions. Is there any question? So Mona Lisa, this is integrated device. That means you have all the functionality there.
Yes.
Can you go back to the main device you have in the beginning? Yes, yeah, that one. So you are using permalloy.
Sorry.
So you are using permalloy as.
Yes.
So what is the main function of the permalloy in this case?
So we are tuning the electrical properties of formula by applying electric voltage.
Okay, so you have continuous, resistance, right? This is resistance change of the permalloy.
Yes.
Versus the voltage. Okay.
We apply the voltage.
Okay, that means this can be extended to much advanced devices like MTG or other things, isn't it?
We have not focused on that part. So now we are tuning the electrical properties in a separate part. We are trying to tune the magnetic properties by electrolyte gating.
So this will bring me to the second question. Why you don't change permalloy with another material that might have very large change of the resistance?
So we have used in the next reports, we have studied various oxide materials which can give higher conductance.
Oh yes, yeah, that's my point. Okay, thank you. Any more question? Now, if no more question, I think we reached the end of this session. I would like to thank all the speakers for their contribution. Also, I would like to thank the organizer of this symposium. And I hope we can see it on a yearly basis in the future. Thank you. So I think we can.
Thank you, Professor Subia.
You are welcome. It's my
There is
pleasure.
a question from Professor Rao. Yeah, please go ahead.
Okay, please go ahead. Yes. Sorry, I didn't see you.
No,
Professor Rao?
question. I was just clapping for all the speakers.
Okay, great. So it was, okay, thank you.
Okay, okay.
I was just applauding them.
Yes,
Okay.
thanks to all of them. Yeah, thank you. And this is the end of this session. Go.
Okay, thank you, Professor Subia. Thanks, thanks to all the participants and
Thank you,
presenters.
Rajit.
Yeah, thank you. Bye bye.
Yeah,
See you
welcome.
tomorrow.
Welcome. Yeah.
Thank you
see
very
tomorrow.
much.
Welcome.